So good morning, students. So all of you type your USN in the chat box. So today I will take up a new chapter under module 2, that is design for fatigue loads. So far we have studied about design for static load, design for impact load. Under static load, we have designed the machine components subjected to compressive load, tensile load, torque, bending moment, likewise. So from this chapter, so we'll understand how a fatigue load is having an impact on the design of machine components. So just I will discuss the introduction about the fatigue load. See, in a static load condition, a load is applied gradually, and there is sufficient time for elongation of fibers. Okay, and the failure of the component happens by means of elastic deformation and general yielding, and ultimately by means of fracture. Whereas in case of fatigue loading, the load is repeated cyclically. Okay, so the load is repeated cyclically. So just take an example of a thin wire, mild steel wire. See, if you want to break that wire, so you can break it by applying tensile load or compressive load, whatever it may be. Suppose by hand itself, if you want to break it, a thin wire, you apply bending moment to it. Is it not? Once you apply the bending moment to it, for a single cycle of loading, it will not break. So repeatedly, you have to apply bending moment, positive, negative, positive, negative, positive, negative. Okay, so for a certain period of cycles, that wire breaks down. So that is called fatigue. Clear? And this fatigue, it's a nothing but it's a repeated kind of loading condition, and this fatigue failure begins with a small crack. Okay, as I said, taking an example of thin wire. Okay, repeatedly you have to apply the bending. Above, below, hugging and sagging movement. You have to apply it repeatedly, and over a period of cycle, so it will break. And this fatigue failure happens with a small crack which is initiated from the component, and the regions of discontinuity such as holes, notches, grooves, and keyways, and the regions of irregularities in machining operations such as inspection marks, stamp, scratches, etc. And also a few internal defects such as voids, cracks, and non-metallic inclusions are also responsible for this fatigue failure. See, most of the times when a body is subjected to tensile load or a compressive load, so that body gives you an indication of failure. But when a body is subjected to fatigue failure, it gives no indication. It gives no indication. It is it's a sudden fatigue failure. Okay, and this failure factor depends on a number of cycles being the body subjected to loading, the mean stress, the stress amplitude, stress concentration, residual stresses, corrosion, creep, and various factors. Okay, so these are all the factors responsible for the fatigue failure. So before going for solving the problem, let us understand the basic terminologies associated with the fatigue, because so we have to understand the various technical terminologies associated with fatigue in order to solve a problem subjected to fatigue load. So when a load or a stress on a machine part changes in magnitude or direction, or both in direction, so the variations are observed in the following conditions. So the first one is stress variation observed on only on the positive side, and the stress variation which is observed in both in positive and with the zero minimum stress, and variation with the both positive and negative directions. So these are all the three conditions which are observed in case of fatigue load, or in other words, you can also call it as variable load. Okay, so why it is called variable? Because the load magnitude is changed from positive to negative and negative to positive, like that. Look at this figure. Okay, so I have three figures here. Figure 4.1, 4.2, and 4.3. So this is 4.1. It is purely a positive load is being applied onto a component. In the 4.2, positive load with minimum stress, that is zero, is applied. Whereas in case 4.3, so both positive and negative load is being subjected to a component or a specimen. And also we have a few more figure in it. So figure 4.4, what is this indicates? So figure 4.4 indicates that equal stress variation both in positive and negative direction. So whereas in previous case, so in figure 4.3 we have positive and negative forces being applied, but this positive force having a major portion on it, whereas negative is lesser portion. So whereas in figure 4.4 it indicates that the load is equally distributed. I mean the positive and the negative load is equally distributed into a specimen. And the figure 4.5 indicates the stress variation on the negative side, purely on negative side, with zero maximum stress. With zero maximum. Look at this. This stress amplitude is attached to this zero line. This indicates stress variation on the negative side with zero maximum stress. And the figure 4.6 indicates a stress variation only on the negative side. So these are all the six cases of loading condition in case of fatigue loading. So that is being demonstrated in the figure 4.1, 4.2, 4.3, 4.4, 4.5, and 4.6. Then coming to the definitions of the terminologies, a stress cycle. Okay, so when I call stress cycle, you should understand that stress cycle is the smallest portion of the stress time plot, which is repeated periodically and identically. Stress cycle is the smallest portion of the stress time plot, which is repeated periodically and identically. Fluctuating stress. uh, Fluctuating stress. So the stresses which vary from minimum to fluctuating stress, the stresses which vary from minimum to maximum value of the same nature. Suppose if I apply tensile load or compressive load are all fluctuating stresses, okay, but which is having the same nature, minimum to maximum. So that is being observed in figure 4.1. And the maximum stress, that is sigma max, it is the largest algebraic stress in a stress cycle. So largest algebraic stress in a stress cycle is considered to be maximum stress. So whereas in case of tensile stress, it is taken positive, and whereas in case of compressive stress, it is taken as negative. Then minimum stress, it is the smallest algebraic stress in the stress cycle. So what is the stress cycle? So this is the stress cycle. What we have indicated. This is the stress cycle. Positive, negative, like that. The load is acted on the body. Repeated load. Then the mean stress. Mean stress, it is algebraic mean of the maximum and minimum stresses in one cycle. So it is average. It is the average of maximum and minimum stresses in one cycle. So it is given by sigma mean is equal to sigma m max plus sigma minimum by 2. Then range of stress. It is an algebraic difference between maximum and minimum stresses. That is sigma max minus sigma minimum. Say figure 4.77, you can see that a graph is plotted between stresses as time. Okay, sigma A is a stress amplitude on both the direction, positive as well as negative direction, where sigma minimum is the distance between the lowest side of this stress amplitude to the abscissa, and sigma mean is from the mean line. It is a value, it is a distance from the mean line to the abscissa, a maximum to the maximum stress amplitude to the abscissa. Okay, so this is the indication of sigma minimum, sigma maximum, sigma mean. And the stress amplitude or variable stress, sigma a, it is a difference between sigma max to sigma minimum divided by 2. That is sigma max minus sigma minimum divided by 2. And the stress ratio, it is defined as the ratio of minimum stress to the maximum stress in a cycle. That is R is equal to sigma minimum divided by sigma maximum. Then amplitude ratio, it is defined as the ratio of variable stress to the mean stress. That is sigma A to the sigma M. Then repeated stress. The stresses which vary from 0 to certain maximum value are called repeated stress. Anyhow, I will share this study material in Google Classroom. So from next class, I am going to take up the problems related to that. So by that time, we should get familiar with the terminologies of the fatigue. Okay. So I will share these materials in the Google Classroom. All of you just go through this once again and try to remember or memorize the terminologies related to fatigue loading. Huh. So there is one experiment which is used to demonstrate the fatigue phenomena. Okay, I'll show that. Mm, so this can be the SN diagram, that is the stress and life time diagram of endurance limit can be plotted, and this is plotted between for a condition of completely reverse bending stress, for a completely reverse axial stress. That is, we call it as a push pull test. If it is axial test, it is push pull test. If it is bending test, it is rotating bending test. Repeated torsional stress, oscillating stress, or superimposed static stress. This is a experimental setup for conducting fatigue test, and we have this equipment, that is fatigue testing machine, in our BMT lab, basic material testing lab. You might have observed this in our lab. Okay, we have a dedicated machine for conducting fatigue test. The machine is quite simple. Anyhow, power is required. Electric motor is the power source, and the shaft is being coupled with the shaft which is connected to the specimen. Okay, and the load is being applied weight through by means of weight to the specimen, and these are all the bearing houses which carries that shaft, and this is the revolution counter. So it counts the number of revolutions on which this specimen is running, and also you can note on the time. So when this shaft rotates, load is applied to this shaft, and this shaft, because of the load being applied to this shaft, the shaft is subjected to positive and negative force. Because but I observed this, when a body is subjected to bending, the lower side, that is the distance from the axis to the lower end fibers, that will be subjected to compression, and the fibers which are between the axis to the upper fiber subjected to tension. Okay, so like that, when a body is subjected to repeated sagging, it will be subjected to sagging and hogging movement repeatedly. The body experiences fatigue load. Clear? So this is a setup. And you can see that in our lab. And this is a graph being plotted with respect to the specimen subjected to fatigue loading. So a graph is plotted between fatigue strength on the y-axis and the number of stress cycles on x-axis. Okay, so look at that. The graph is coming down. What it means, as the number of cycle increases, the fatigue strength of the material decreases and leads to fail. Okay, so initially, when at lower cycles, the fatigue strength of the body of the component of the specimen is very high. As the body undergoes repeated fatigue, it loses its endurance strength, and gradually the endurance stress value decreases with the increase in number of stress cycle, and at one point of time, the material fails. Okay, so this life cycle can be classified into two cycle, that is lower cycle and higher cycle. So just observe here, when a body is subjected to 10 raised to 3 cycles, okay, stress cycles, so that cycle is considered to be lower cycle, and beyond that 10 raised to 3 cycle, it is considered high cycle. Up to 10 raised to 7, it is finite life. Up to 10 raised to 7, it is called to be finite life. More than that, it is infinite life. So this is the general behavior of the material subjected to fatigue. So as the number of cycle increases, the fatigue strength of the material decreases. Effect of factors on endurance limit. So endurance means this is the term associated with fatigue. Okay, endurance limit means this is the endurance limit. In the graph itself, I have explained it. Okay, so this is endurance strength or endurance limit, hmm, that is plotted on y-axis. So particularly in case of fatigue, we use this term endurance. Endurance, it is the ability of the material to withstand the fatigue load. Okay, and this endurance limit of material strongly depends on the following factors. First one is type of load. Second one is the surface condition and corrosion. Third one is the size of section. Fourth one is the grain size and direction. And fifth one is the discontinuities in the section. It could be holes, notches, fillets, etc. In the operating temperature, heat treatment, residual stresses, and a type of cycle and a type of stresses. So these are all the factors which affect what? The endurance limit of a specimen. Surface condition. Ha. See, whenever a body is subjected to fatigue load, surface condition plays a vital role. Okay, so you can see this graph. This graph is plotted for various surface conditions. So look at this. Considering mirror polished, you got some value. Polished and grounded, machined, scaly surface, hot rolled, corrosion in fresh, forged, corrosion in seawater, like that. Okay, and a surface coefficient factor, that is ESR, is plotted on other side. Sigma ultimate is plotted on x-axis. So what it indicates? So this fatigue is dependent on various surface factors. Okay. So suppose if a body is mirror polished, its value is something. If a body is polished and grounded, its value becomes a little bit low. Scaly, lesser, little bit less. Forged, less. Corrosion, much more less. Like that. Then size effect. So this is the effect of surface. So you can just go through this. This is the effect of surface. So then the size of the specimen also matters in case of fatigue. And one important note to be observed in case of surface condition is that For a mirror polished specimen, the surface correction coefficient ESR is considered to be 1. So in the problem they mentioned that the surface condition is mirror polished. So in that case you should consider surface correction coefficient value as 1. So you should remember this. Then size effect. The standard test specimen used in a rotating beam method has a nominal diameter of about 7.5 mm. If the nominal diameter is not equal to 7.5 mm, the size correction coefficient, we call it as ESZ. ESZ or in some other data handbook, it is represented by B, should be considered. Okay. If the nominal diameter is not equal to 7.5, you should consider the size correction coefficient, that is ESZ. And this fatigue strength has been observed to decrease with increase in machine part size because of the following reasons. So what are all the reasons? So with the increase in size of the part, the probability of increase in internal defects are more. So if the size of the specimen is more, the probability of internal defects is also more. And there is a higher probability of initiation of fatigue crack because of the larger area. So area, it contributes to the initiation of the fatigue crack and also the propagation of the fatigue crack. Difficulties in obtaining uniform strength and heat treatment throughout the whole cross section. Okay, so in order to, in solving the problems, we consider this size correction coefficient. Okay, and the graph shows its size correction coefficient with respect to the sizes. So for 40 mm, 80 mm, 120 mm, 160, 200 mm, the considerable size coefficient values are given over here. So these values are available in the data handbook. So you can consider that. For example, take an example of for 160 mm. So its value is around 0.6. The size coefficient correction factor value is 0.6. Suppose if it is 200 mm, suppose if it is 80 mm, so its value is nearby to 0.8. Okay, so like that. If its value is 40 mm, it is almost equal to the size correction coefficient is equal to 0.9. So like that, you should choose the value based on the size of the specimen, and you should incorporate this size correction coefficient in solving the problem. Then after that, see, these are all the values. Look at this. This is taken from the chart. If its value is 7.5, consider it is 1 equal. If diameter of the specimen is 7.5, you should consider the size coefficient as 1. And if its value between 7.5 to 50 mm, you should consider 0.85. If its value is more than 50 mm, you should consider 0.75. So that is the size coefficient factor. Then apart from that, we have effect of load on endurance limit. That is considering the load correction coefficient. So we have seen a size correction coefficient. We have seen this one. This is size, the surface correction coefficient. Now it is load correction coefficient. So what is the effect of load on endurance limit? See, this endurance limit, that is represented by sigma minus 1 of a material, is determined by rotating beam method, and there are many machine members which are subjected to loads other than reverse bending, and therefore endurance limit will also be different for different types of load. So while considering a load correction coefficient, if it is 1, it is considered to be 1 for reverse bending condition. So you should remember this value, that this load correction coefficient value, it is equal to 1 for reverse bending load, and its value is 0.7 for reverse axial load, and its value is 0.6 for reverse torsional load. For reverse torsional load. After that, one more factor, that is the effect of reliability on endurance limit. So reliability means the service of the material for over a period of time, it should perform without any breakdowns. That is the reliability. Okay. and this coefficient of reliability depends on the reliability that is considered in the design of the component. Okay, so reliability of the fatigue test is 50%. It is this value is it is taken from conducting series of tests under fatigue condition, and this reliability coefficients are based on a standard deviation of 8% as follows. Suppose if you consider reliability as 50%, you should take that value as 1. What value? Reliability coefficient value on endurance limit. If its reliability you consider it is 90%, so you should consider ER value as 0.897, 95.868, 99.814, 99.753. So all put together, one more factor, that is effect of concentration on endurance limit. So we have seen the effect of stress concentration. See, the stress concentration, the outcome of stress concentration is it induces the crack, and initiates the crack, and also the crack propagation takes place at the junction of the high stress concentration. So even in fatigue also, this stress concentration will have an effect, so you should consider that effect also. So that is designated by K minus sigma. Okay. So this is the effect of stress concentration, and this K minus sigma is called to be stress concentration factor. Okay. It is a ratio of sigma minus 1. Sigma minus 1 is endurance limit without discontinuity, and sigma dash minus 1 is endurance limit with discontinuity. So why we have considered discontinuity is we know that the stress concentration happens only in a place where discontinuity is there. So just consider take an example of a plate. So if you apply a load to a plate, the stress is uniformly distributed. Suppose you make a hole on a plate and apply a load, the stress concentrate at the vicinity of the hole junction. So that induces what? Stress concentration. So now we are considering the stress concentration effect in solving fatigue problems. So you should consider a factor that is called as stress concentration factor. What is this? It is nothing but the ratio of the endurance limit without discontinuity to the ratio of to the endurance limit with continuity discontinuity. Okay. So all put together, we have so far we have discussed surface correction coefficient, we have discussed size correction coefficient, load correction coefficient, reliability correction coefficient, and also stress concentration correction coefficient. So we will incorporate all these coefficients, correction coefficients, whenever it is necessary in solving the problem. Okay. Next is fatigue strength under fluctuating stresses. So I will discuss about this topic in the next class. Okay. So what is the effect of fluctuating stresses in fatigue strength? We'll discuss in the next class. So today what we have discussed is we have discussed the definition of the fatigue, and what is this fatigue, how it is differentiated from other kinds of loading. It is a tensile loading, compressive loading, bending, torsion, and what is the behavior of the material with respect to the fatigue load. We have discussed with a graph which is plotted between the number of cycle versus the endurance limit. Later we have discussed about the various correction coefficient factors. Okay, surface factor, size effect factor, and then effect of load factor, reliability, then stress concentration. Okay, and in future we will see how all these correction coefficient factors are incorporated in solving the problems. So with this I will end today's session, and I have shared the impact load notes to the Google Classroom. Just use it for your test, and if you don't have any doubts, I will end up today's session. So I believe all of you have entered your ASN in the chat box. Okay. So with this, I'll conclude today's session. Thank you. Thank you, one and all.